All the gray vectors you see on the screen have been scaled by 2 and also rotated counterclockwise by 30 degrees. It means that every vector is transformed into a new vector, which is shown by t of v. Suppose that we have two vectors v and w on a 2D plane. This yellow vector represents the addition of these two vectors and is another vector in the same vector space. We are going to scale all of these vectors by 2 and also rotate them by 30 degrees. This is called a transformation. T of v is the new vector under this transformation. In fact, vector v under this transformation is t of v. This is the transformed version of the other vector w under this transformation, and the transformed version of their addition is shown by this yellow vector. Notice that the addition of transformed versions of v and w is equal to the transformed version of the addition of the two vectors. Now consider this vector. If we scale this vector by a scalar alpha, which is a real number, we get this yellow vector. Now, if we transform v using the same transformation t, we get t of v. And by scaling it by the same scalar alpha, we get this new vector. The amazing thing is that this angle between alpha v and alpha t of v is again 30 degrees. And if we transform the scaled version of vector v, which is alpha v, we get the multiplication of alpha with the transformed version of v itself. It means that this transformation preserves a scalar multiplication. We define a transformation from a set v to another set w. In other words, under this transformation, an element v in the v transforms into another element t of v in the set w. If the two sets are not just sets but also vector spaces and the transformation preserves vector addition and a scalar multiplication, we call the transformation to be linear. Linear transformation is also called vector space homomorphism or linear mapping, and it is a very important concept in linear algebra. For every two vectors v and w in a vector space, and for every two real numbers alpha and beta, a transformation is linear if it preserves vector addition and a scalar multiplication. What you see on the screen is just another way of what I showed you with the geometric vectors in the beginning of this video. A really important result of this definition is that the transformation of the zero vector is the zero vector itself. As you will officially see later in this video, this one is not a linear transformation because the zero vector is transformed into a vector which is not the zero vector, so this is not a linear transformation. Pay attention that this one is not also a linear transformation, but it gives the zero vector under the transformation, so we have to take more things into consideration. Let's investigate this example in the beginning of the video with more details. This is a linear transformation from a two-dimensional vector space to another two-dimensional vector space. If we multiply each vector by 2, it means that we are scaling the vector. Scaling a vector is an example of a linear transformation. Also, rotation is a kind of linear transformation, and as I have talked about rotations and their matrices on this playlist before, you might know that a rotation on 2D plane can be shown by this square matrix. So, a 30-degree rotation does this to a vector and changes it into another vector that you can see on the screen. As a consequence, if we scale a vector by 2 and also rotate it by 30 degrees, we get the relation for this linear transformation you saw in the beginning of the video. Don't worry about this matrix, which is the matrix representation of this rotation, because I'm going to talk about matrix representation of linear transformations in another video. And on this video, you're just going to see different kinds of examples of some transformations that are linear and also some other that are not linear. So you can distinguish between linear and non-linear transformations. So let's use the definition of linear transformations and prove that this transformation is linear. This is a definition. So if we take these two vectors v and w that are represented by two numbers in a column matrix, or aka column vectors, we can first add the two vectors and apply the transformation on the addition, which gives this column vector. We can easily separate it into the addition of these two vectors. This is the addition of the transformed version of each vector, which shows that this transformation preserves vector addition. Also, if we first multiply vector v with a scalar alpha and then transform it, we see that alpha can be factored and written as a multiple of the transformed vector v itself. This shows that the scalar multiplication is also preserved, and this is a linear transformation. Another interesting example of a linear transformation is from the set of all the 2D vectors to complex numbers. Both of them form vector spaces. This transformation gets a 2D vector and transforms it into a complex number, which is also a vector. That is why we can represent complex numbers using vectors on a 2D plane. Pay attention that complex numbers have more structure with them and can also form a field like real numbers. So if we add two vectors and then change them to a complex number, it is exactly like transforming two vectors to two complex numbers and then adding them. Also, if we scale a vector and then transform it into a complex number, it is exactly like transforming the vector into a complex number and then scaling it. Another example is projection of a 2D vector on the x-axis. As you can see, projection on the x-axis preserves vector addition and also a scalar multiplication, which means that projection of a vector on the x-axis is a linear transformation. We saw in this video that all polynomials of degree n and less can form a vector space. And I also told you that a derivative is a kind of linear transformation for this specific kind of vector space, which transforms polynomials of degree n or less to polynomials of degree n minus 1 or less. As an example, P3 shows all the polynomials of 3 or less and can be written in this form. The derivative of these polynomials gives polynomials of a degree less than the previous. So if we add two of these polynomials and then take the derivative, we get this expression that can be separated into the addition of these two expressions. They are simply the addition of transformed version of the polynomials. Also, if we multiply the polynomial with a real number and then take the derivative, it is exactly like taking the derivative and then multiplying it with the real number. So, derivative is also a linear transformation. Now, let's see an example which is not a linear transformation and see what happens. If we add two vectors and then transform it using this nonlinear transformation, we get this column matrix. As you can see, we get a different result if we first transform the two vectors and then add them. So this transformation doesn't preserve vector addition. Also, if we multiply a vector with a real number and then transform it under this transformation, we get a different result as transforming a vector and then multiplying it with a scalar, which shows that this transformation doesn't preserve scalar multiplication. Another example of a nonlinear transformation that preserves the zero vector is this. This is the transformation of addition of the vectors. It is different from addition of transformation of vectors. And this transformation doesn't preserve vector addition. Also, this transformation doesn't preserve a scalar multiplication and gives away alpha squared instead of alpha. You can check yourself that these transformations are also non-linear. This one maps a 2D vector into a real number, which is the distance from the origin. This one folds the plane along the coordinate axes. And this one sends every vector to the same point.